Okay, any question from the last lecture from yesterday? For assignment, right? I think we're gonna delay again because I think only this today will finish everything you needed for the assignment. So you have any idea why you want to delay the assignment? Next Wednesday. Next Wednesday. Okay. So if you have problems, please come to office hour, okay? Wednesday 8 to 10, okay, with MAT study group, okay? And A4G11. Okay, A4G11. Hey, Rachel, you want to promote your AI? You change day. And then Friday. Okay. You want to promote or not? For next Friday, huh? Oh, maybe this week and later they decide to part two next Friday, then you do. Okay, okay. Okay, never mind. Okay, up to you. Up to you. Okay. So there's some bookkeeping. So we continue with cardinality. After cardinality, we will start matrix spaces. Okay, matrix spaces. And then I think you will see a lot of similar thing with MA2 soon. Okay. And I think in my latest lecture, I accidentally deleted this slide about an index set. Okay, so index set. So what is index set? Last time we say let I be an index set. Okay, then we can label set the set as, for example, AI such that I is in. Okay, so index set is just some set we use to label a set. Okay, for example, can you think of a real life example of index set or not? Seng. Can you think of a real life example of index set? How do you label items? 听得懂我问什么吗？给一个 example 呢？就是你拿来 label 东西的东西，对吧？对吧？是这样讲。你来标记的东西，然后用什么标记？所以我要你，我要你想一下，想一下。嗯嗯，货仓里面的东西需要标记吗？货仓 garage 啊，OK，价格也是一个标记，right？ So 价格 is a set of what? Set of numbers，对不对？你用 numbers 来标记你的货物。Yeah, so those are index set. So you can define your index set as a function, okay, as a function. So let's say you have a non-empty collection of set. So meaning, let's say you have a lot of items. An indexing function for these items is a surjective function from some set I. Okay, this I is what we call index set. So just now we indexed our item using numbers. So I are numbers. Okay, and then the collection of the item, the set, together with the indexing function is called an index family of set. Okay. Then for each I, okay, for each price, you have a item. Okay, for each price you have an item. Okay. So in this case here, it's slightly different from your price. So price, for example, two items could have the same price. Fair enough. For example, what? For example, what? What are the two items that have same price? Milkshake ice cream and Bingshake ice cream is the same price. Okay, but when we try to do labeling here, right? This is for each I have a AI. Okay, each I have a AI. Right, so every I you have different AI. Could be the same AI, okay, could be the same AI, but each I attached to a one AI. Okay, this is the function. What function means, right? Okay. All right. So so what's the use of suggestion here? Suggestion just says that every elements in I you're gonna label by some element in the index set. Okay, so this is called the surjective function. By the way, this line is not finished yet. I finished it in my other notes. So if you read set of A alpha, right, such that alpha is in J, we'll call it the family of all A alpha as alpha ranges over J. Okay. Sometimes we put this alpha in J inside this set, sometimes outside is the same. Okay, it's similar. Okay, no, should I write it up for you? Okay. Then sometimes we write this A alpha such that alpha in J. Okay. All right. One more thing. Okay, one more thing about function. Let's ask you about this. So one more thing about function. So we know that function is from t to s, right? Two set. Okay. Let's say my t is empty. Can I define a function from an empty set or not? What's that function? Uh, 中意啦，该点到中意了。Okay. 来中意。What's a function from an empty set to any set? Function says what? For every element in the domain, right? Nothing there. How to define? Can you do anything 能够做什么嘛？能够做什么？不能够。Okay. One way to see this function is you see it as a tuple, right? So you see it as a tuple, let's say x, y from empty set cross S. Is it possible or no? No elements like that, right? So no elements satisfy this set, meaning what? This set is empty. And then this is what we call the empty function. This is called empty function. Okay, empty function. Okay. So there's only one way you can map out from empty set. There's only one way. It's the empty function. Okay. So let me detour a bit. Detour again. We will say that empty set is the initial object in the category of set. Okay, category of set. Initial object, meaning if you start with phi, there's only one way to get to the other thing, other set. There's only one way, which is the empty set. Okay, there's only one way. Initial object. There's another thing in the category called terminal object. And to guess what it means? Terminal. Initial means there's only one way to go out, right? Terminal, there's only one way to map into things. Okay. Very interesting. Yes. What do you think? What do you think? What do you think? What's the terminal object in category of set? Unset? Sounds right, singleton set. Sounds right, I think. I think sounds right. You check it. You check it. What's the terminal object in category of set? Have you checked it? I think sounds right because everything gets sent to one thing. But let me think. Yeah. What's the terminal object in the category of set? Singleton? Singleton? Or is there a terminal object there? Huh? Singleton? Sounds right, singleton, because there's only one way to map into singleton, right? Everything have to go to that element. And there's only one way. Sounds right. But anyway, it's not important for this class. Just some extra knowledge for you. Okay. So next theorem. How big is R2? How big is R2? How big is R2? Hi, Ivan. How big is R2? What do you think? How about think about how big is R first? C, huh? How about R2? Wow. C square. Sounds right, eh? But actually it's not. So R square is just as big as C. Okay. Yeah. Sounds right, but not. Okay, so how can we show it? How are we going to show it? Let's do the proof. So if we're going to prove that it is as big as C, right? So meaning you need to form a bijection with something is as big as C. What are the things that is big as C? R, what else? 还疑心，还有什么东西是跟 C 一样大的？有人讲 R 的 ，R 和谁一个人？还有什么跟 R 一样大？Sorry，01 open interval，open interval 0 to 1，OK，还有呢？Any interval actually, any kind of interval, open, close, half open, half close, are all the same. 有吗？还有其他吗？啊，来讲一个，叫什么？昨天说了哎，好几个。大家我刚听到对的答案了，你再念一次看。对呀，equation 呢？对呀，equation 呢？我们昨天有说，但那些有点太复杂了，OK？So we just focus on open interval 0 to 1。OK， we just show 0 to 1 cross 0 to 1 is equivalent to 0 to 1. Okay, now we're going to find bijection. Okay, we're going to find bijection here. Let's define a bijection. Maybe this is not bijection yet. Let's see how we can do with this. All right. So let's say we have a function defined like this. So if I take an element from this product set, I can write it in the decimal expansion. Decimal expansion. Okay. Can I produce another number in 0, 1? What do you think? Jack? If I give you 2 decimal expansion, can you produce another? Okay, we can like how do we say this? Stack them together. So on. Where we want to avoid taking infinite string of 9. Okay, that's the technical point. We don't want infinite strings of 9. Okay, this function is one-to-one or onto or not? It's one-to-one. Why? That's right, one-to-one. If S1, Y1 not equals to S2, Y2, right? They should have different decimal expansion. Okay, then the way you put it in should be different. Okay, it should be clearly one-to-one. Okay, but is it onto or not? Onto or not? Onto me? Let's say we put one number 0.919191919191919191. What happened under this map? Huh? What happened if I get a 0.9191919191? What happened? What's the pre-image? 来看下谁会。若兰 what's the pre-image for this 0.919191? What's the pre-image? What's this pre-image? How you split them? One with X and Y, two. Give me the two number here. What is the SY that gets sent to 0.9191? Repeat. Do you understand this map or not? Do you understand this map? You take S1 from the first digit of X, and then Y1, the first digit of Y, and then second digit of X. What do you mean by 91? 0. What? Your X is 0. What? You understand this map or not? Do you understand this map? So you got an X, you got a Y, right? Okay, and then you stack your Y1 behind your S1, and then insert Y2 behind your YX2 to get this image here. You can see or not? And then where is 0.1? Like this, 0.1, 0.9. Switch. That is, in this case, I think you only get 0.9100000000, right? So what you need to do? Then the other one, 1. Okay, but not that we don't take this expression, right? This is equal to 1. Okay, we don't take infinite string of. All right, so you can see that this is actually not onto. Okay, so at best, what we have shown is there's an injective map from 0, 1 cross 0, 1 to 0, 1. Okay, so we need the other direction. Well, we need the other direction. So let's define the other injection. like this. So how we're gonna do is send Z to just Z, comma 1 over Z. Okay, that's all. This is an injection. Injection. Inject, right? Does it work or not? What up? What not? 1 over Z. Does it work? Why? Why cannot? Z is from 0 to 1, and then 1 over 1 over 2. What do you mean by 1 over 2? Uh-huh. Sure. But the problem is 1 over Z in 0 to 1 or not? No, man? What do you mean 2, 2, 2? What do you mean 2? That is, oh, okay, 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 okay. So how to do? What to do? So how? Huh? What do you mean? Oh, just one. Just like this. Hey, wait, wait. I'll just send to this. I don't know. Is it better? Yeah, we just need injection. Just inject into one of the coordinates should be enough. Okay. Okay. So G is 1 to 1. Since if Z1 not equal to Z2, then Z1 comma 0.5 is not equal to Z2 comma 0.5. Okay. So hence we have an injection from 0, 1 into the product set of 0, 1 cross 0, 1. Okay. 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 So what time is it? 3 to 5? Yeah, problem. Okay. Why? What do you want to write?
Because I think if you consider applying to 0.099 and this is 0.1 and another point to 0.
We don't want 0.999, right?
I think this will cause a problem.
No. We don't want this kind of number to exist actually. If you want to do 0.09999, we just consider 0.1.
Oh, okay.
We just choose one of the representative. We don't want the string in that line.
Okay.
Okay. Wait, so what's the problem if you include these two?
You will find that this this is the two expression two numbers.
So you see, if I include the two way of expression, this two will send to different number. Anyone recognize? Lydia, I want to try one. First one, what do you get? 0.09191 like that. Okay. How about second one? 0.111. Yeah, these are two different numbers. Yes. So if you include the same number with different representative, actually you get different number. Okay, so we just pick one. We don't want the one that end as infinite string of 9. Okay. Pick one is enough. But we choose not to take the infinite 9. Okay, right. So theorem, how about Rn? How big is Rn? C. Okay. How are we gonna show it? Induction. We only got base case. How to how to induct on general n? Okay, so instead of asking you to do this, we will do an even more general one. Okay, so we will prove that this set here are infinity. Okay, we just go all the way to infinity. And then these elements are the sequence actually, x1, x2, blah, blah, blah. Okay, this set here in particular also is equal to C. Okay, we're going to use this proof technique. Then later you can apply to the finite n. Okay? You can terminate. Yeah, you can terminate the method we use here. All right, so how to do that? Let's see. Let's see. I think you will see a very familiar method here later. So let's see what we have. So we will reduce our case to only points in 0 from 1 also. Okay, so let's reduce to this ball here. Okay, we call it a ball, B. Later in this course, you will see a lot of ball, a lot of lovely balls. So tomorrow, why? Balls, yeah, open ball, I mean, open ball, closed ball. Actually, they are not really circle or sphere for the ball that we want to consider. Later I will show you. Okay, there are different shape of balls. Okay. Right. So let the ball be a sequence of numbers such that these terms are coming from the interval 0 to 1, open interval, okay, for OI. So what we're gonna do is we're gonna reduce to this infinite product of balls. Okay. So recall that we have open interval is as big as R. Okay, so in this case here, we also have B is as big as R infinity. Okay, this one we could use what we proven yesterday, but this is an infinite argument here. So it is suffices to show that this ball here is as big as C. So if you want to show something is as big as C, right, you need to compare to something as big as C. Okay, so the easy things to compare to obviously is the open interval 0 to 1. Again, we need to build a map between 0 to 1 and this B here. Okay, I think this direction is easier. This direction is easier. Okay, what can you do? P is infinite terms that's in between 0 to 1. But now I give you an element inside open interval from 0 to 1. What can you send this x to? Which point you can send it to? Constant sequence. Okay, you just send it to x, 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 x. Okay. Is it obviously injection? If x equals not equals to y, obviously the constant sequence x is not equal to a constant sequence y. Okay, so got that. P is an injection. Okay, so we had the cardinality of 0. The open interval, the cardinality of open interval from 0 to 1 is less than or equals to the cardinality of B, which is less than, which is greater or equal to C. Okay, how about the other direction? Can we show the other direction? If it's surjective, then you are done now. Obviously, it's not surjective. So let's do the other injection. If you are given an infinite series here, what to do? Okay. Let's take this element inside B. Okay, so you have a bunch of 0 point something, 0 point something, 0 point something. Can you produce another number in between 0 and 1? How? Want to try? Sorry? What do you mean by geometric sum? Wait, how do you deal with this SI? Sum them out. Sum? Oh, wait, so you say x1 plus what? Like this? Good 9. The geometric. So let me try. What do you mean by this? Okay. 1 over 3 to the n s and n minus 1, like this. S1 over 1, right? Huh?
I think we need equal.
1 over 3?
Yeah, to make it smaller.
You mean this one make it smaller? So here is 9. Here is 27. And then, so does this converge or not? Conversion. How to show this conversion? Okay. Wait, let me see. Wow, calculus 1 or calculus 2. This is less than or equals to this, right? Sum 3 over n. By geometry theory, it converge. Okay, I think it works out. Really smart. But is this injective or not? How do you work it out? You want to suggest, you want to find an epsilon. You need an epsilon. Okay, let's try first. So suppose x is not equals to y. So how do you show that? So I want to show that sum of n equals to 1 to Sn over 3 over n minus the sum here is greater or equal to sum absolute. Is it possible? Or I mean absolute values, because I don't know which one is bigger. So how?
The first figure from the
the
first figure is different. It's the ice figure.
Okay.
I think the difference is only by straight minus ice.
Bounded below.
But I mean,
Bounded below.
Yeah.
Is it true? Let me think.
Like how the tail up is going to easy.
This one I think needs some argument. Can you try and write it out? I think there's some argument need to some argument to be completed. Can you try and write it out? Try and write it out. Send me after the class. Okay. So yeah, try and complete this. Sounds a very good plan, but need to show that it's injective. If how about the method I mentioned before, a familiar method for you. So let's try a second method here. Sound nice, I actually use the geometric one. It's going going into analytical way. Okay, let's try a familiar way. Okay, if we can have the sequence here, well, we can write each xi as their decimal expansion. Okay, so we write them as their decimal expansion. Does this looks familiar or not? Doubly infinite thingy. Now we want to combine them. Seems like we do this trick for the third time already. We got a doubly infinite sequence here. Want to combine them into one number. We can define. Wait, fine. Let me write down the magic first. Then see if you can recognize or not. 0.x11, x21, x12, x31, x22, x13. What's this? Huh? Again, the enumeration of your rational number. Go down, go up, go up. Okay. Yeah. Okay. So this is an injection. Okay. From B to open the verb from 0 to 1. Okay. Yes. Yeah, similarly, yeah. Yeah, these are the technical points you need to impose. Okay. Yeah, avoid. Over here, make sure you avoid infinite string of line. Okay. Okay or not? Got question? Yes. You want to comment on geometry series? Yeah.
I think I let x1 equal 1/6, then x2 equal 1/2. And separately,
Wait, so you say put a 1/6 here, and then 1/2 here, and then and then it's okay.
Something like that. Just like
1/18.
Yeah, just you can put correct number x1, x2. Then that front part will be the same. Something.
Oh, you mean it's not injective? Or you're suggesting this might not be injective? Yeah, if it's not injective, you need to produce two sequences. Your suggestion? What do you mean 1/3 only? Then what's the next? You need to produce the infinite sequence. But you guys want to make it 1/18 all the way. Is this what your strategy? Okay, you work out first. Let's see how. Okay, so can you see from this method how you prove for Rn? What's the difference of Rn and R infinity? For Rn, the tuples will terminate. Okay, you just stop at some Sn here. Okay, then obviously you can use this method, this snake method, to enumerate. Does it make sense? Okay. So if you just stop at random n, you still can use the similar technique here. Okay? Does it make sense? Make sense or not? 懂我讲什么吗？如果这个 sequence 暂停到某一个 Sn， 你还是可以这样子排。也可以更简单的也可以。Okay. So you can just go down and go up, go down and go up. Right? This is what Eric says. Okay. 看吗 ？OK 了。Why we cannot do this go down, go up for infinite 这个又是个问题。What if this is going down infinitely, right? Why not we go down 无限 and then come up? Okay, so I give you one example. Can I write like this? 0.x. Hey, I write like this. Got student write like this. This got students write there. So you take note. X1, X21, X31, X41, blah blah blah, and then attach X2. Sorry, X12, X22, X. 有人这样写全部人看盯这个我考试不要看到这个。现在我解释给你听，就会这样写。OK， if write like this 有什么问题哦？有问题吗？你觉得？没有问题啊。OK， 有问题的讲一下什么题？呀，什么叫做无限装在有限的中间啊 ？What's that? What's the infinity in between and finite? Where should I put this one to? 我去哪里找？你问我去无限找啊？哪里是无限？我去哪里拿？去无限在哪里 ？Cannot. This is not certain. Don't know where to put. Previously is very certain. Okay, there's a way to go. I know the previous one is what. The previous one is what. And then I know where to start. Most important. Okay. But here don't know where to end. Already want to start already. 对不对？会做这样的。Okay. Does it make sense? Okay, this is wrong. So here is the ambiguity on where x12 is starting. Okay. The point is we don't know where the infinity going to end. We don't know. Okay, so you cannot do that. So there's an ambiguity there. Okay. Okay, we're gonna do one last theorem for cardinality. Let's do the one last theorem for cardinality here. Hopefully this is helpful for your assignment. I'm not sure if it is, but we'll give you an idea of a power set. So if I take a set, how big is your power set? Power set is what? All the subset of A. For sure, it contains A. Correct or not? A is one of the subset of A. For sure, it contains A. And contain all the other power set. Subset. Okay, so how big is it? Can there be equal or not? No. Why you know? Could be, correct or not? Like what we have shown just now, R is as big as R square, correct or not? But actually, we can show that it is strictly greater, very strict. Okay, strictly greater. So, how are we going to show this? Well, less than or equals to is really easy to show. You know how to show it? Or less than or equal to. What's the injection you can do? Yeah, so between, okay, so let's define injection F from A to positive A just by sending A to the set. This is injective, correct or not? If A not equal to B, then the set containing A obviously not equal to the set containing B because they contain different things. And so this is the injection. So we have the cardinality of A is less than or equal to the cardinality of the power set of A. Okay. How to show that they are not equal? Let's think about it. How to show it's not equal? Okay, so we're gonna show it's not equal by showing that there's no onto map from A to PA. Okay, there's no onto map. Okay, you cannot reach everything in PA using A. Yeah. Yeah. Okay. So we're gonna show that next we are going to show that there's no onto F from A to PA. Okay, now we're gonna do a very tricky stuff. How we started set theory, we're gonna end the set theory the same way. Okay, we're gonna use Russell paradox technique. Danny. So that doesn't exist. That exists slash. Okay, so how we started set theory, we're gonna end the same way. So suppose there is a function, okay, from A to PA, pick any one of them. We're gonna find something in PA that cannot be mapped from A under this F. So this set here gonna depend on the F you give me. No matter what F you give me, I can find something that you cannot map to it. Okay. So this magic set is called the X set. The X. This is everything in A such that A is not in FA. Okay. So not that this guy here is a power set of A because inside there are elements from A. Okay, so it is a power set of A. Okay. Because it is a subset of A. Okay, so these two things says the same things. These one and two things is the same. Sorry. Okay. Right. We want to show contradiction, right? Suppose this X is equals to some FB. Okay, let's say you say that some B can be mapped to this X. Suppose you can do that. Okay. Suppose you can do that. X equals to some FB. There are two ways, right? Because I pick the set X for all the elements from A. So B also in A, right? So either B inside this X or B outside this X, correct? The two possibility only. Because this X are picking from all the A's, right? Such that this is true. And then I got some B from A. So meaning this B either inside this X or outside this X. Two cases. Okay, two cases. Okay. Let's see what happens. If B is inside X, then what? It will satisfy the condition, right? Then B is not in FB. No problem here. Any problem here or not? Excuse me. Any problem here? Think slowly. Any problem here? Sorry? FB is equals to X. But by assumption, we know that FB equals to X. So here is by assumption. You say X, you say B in X, then you say B is not in X. Contradiction. Okay. How about the other case? Let's say B is not in X. Okay. Maybe not in X, correct? If it's not in X means what? Doesn't satisfy the condition inside the set law. Then what? B have to live in FB. But FB is still X. Again, you TCL. Okay, contradiction. This is absurd. Okay. So thus, there's no way for this X to stay in the range of F. Okay, so we found a set that this F cannot map. Okay. Nothing can satisfy this. It's not that nothing. Yeah, it's not that nothing can satisfy this condition, but just this X cannot come from some B. Okay. All right. So one last question before we leave this chapter here. So the question is, yesterday we write down this inequality here, 0 less than 1 less than 2, blah, 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 less than D, less than C, right? So the question is, between C and D, is there something else here or not? Okay, 不知道，高正了不知道。Use your gut instinct。你在这个地球上生活20年，有没有什么想法？有什么想法？啊 ？Is there anything in between here? Between real numbers and natural number， 还有什么可以出现的数字吗？有没有？ Okay. So in other words, is there an infinite set A in R such that there's no one-to-one, there's no one-to-one map from A onto N, and there are no one-to-one map from A onto R. Okay, can you squeeze a number in between C and D or not? Okay. The proposed solution here was for the continuum hypothesis. Continuum hypothesis. So continuum hypothesis says that there's no P such that P is in between C and D and C. It turns out that the current set theory, right, cannot settle this problem. Okay, it's undecidable. They prove it. Proven. OK， 证明告诉你，我们现在的理论不能够讨论这个问题，不是说它对还是错哦，对跟错的不能讨论，讨论不了，讨论不出来。OK， so we need another machinery, okay, to talk about this if you like. So meaning you need to have another framework to talk about these cardinality. Alright, if you're gonna use just the set theory we produce, it's not enough. Proven cannot decide. 我不知道是对还是错，但是你被证实，你不知道，你不可以知道是对还是错，不能知道很痛苦这给数学家。数学家 for mathematician, a statement we either want to know it is true or false. There's only two possibilities. Okay? That's why I like maths a lot. So if you want to know this, you need to put in a broader context. Okay, in a broader context. Maybe you need a more sophisticated theory to talk about them. And then in that theory, maybe you can produce something in between C and D. Hopefully. Okay. No? Actually, this is related to the Gödel's incompleteness theorem. Okay, what does the Gödel incompleteness theorem does? And this is a very important thing you need to know in logic. What's incomplete? Okay, so this incomplete is incompleteness about a theory. In every theory you produce, you can produce a statement that cannot be proven in that theory. 懂什么意思吧？每一个理论里面，你都可以造出一句话是你不能证明的，很可怕哦。 怎么证明这句话？Okay. So you actually need extra theory to prove something that you cannot prove. So that's why research work That's why 你们不是问一个问题吗？什么东西都找了哦，还有东西好，还有东西好研究咩？有 Goddess incompleteness， 确保了你有工作。OK， 研究不完的，你一定找到一个东西是现在的东西解释不了。OK，understand？OK，有工作做啊，不用怕，来做研究啊。OK。Okay, so let's take a break. Let's break until 4:07.
Yeah, we need a little more bound on the something. If it's a interval, it's not work.
If it's
because my idea is that since you are different from the ice and everything else, I think it would be there will be a lower bound. But actually, the difference between xi and yi can be arbitrarily small.
Okay, be arbitrary small.
So anyway, it's just simply because it's from the interval. Yeah.
Okay.
If it's from a discrete set, definitely can.
Okay.
Binary.
Yeah.
Binary. Okay.
Yeah, contact example.
What kind of example?
Yeah. Xe 1/3. 1.
Oh.
Yeah.
Okay.
Yeah, it's
It's
bad.
not injective.
It's
Okay.
bad.
Okay.
Yeah.
Okay.
Yeah.
Can include this also. Fine. See you.
Okay. We can have something that is, I mean, not comparable, and everything has a distance between each other. Something like also that's workable. Yeah, that's okay. Yes. Yeah.
Right, let me think. So I mean, if you have discrete set,
I mean,
this SOB is. I mean, for all these choices, you only have discrete choices.
Yeah, I mean, my
But I
idea
mean, these two are discrete also.
actually. Yeah. We need something like the very strange thing.
Okay.
It need to be not countable.
Not countable.
Not countable because we need the kind of the argument, right? Otherwise it's useless. Not countable. And then
Why is not countable? You mean this
0 1 something like that.
this set is not countable.
I mean 0 1 the domain is not countable because we want to show it's equivalent to R, right? Yeah. So it's not countable, and everything has a distance between each other, and the distance has a lower bound and the upper bound, and the lower bound should be
depend on what series you use. The bound should be depend on what series you use.
The bound should be for everything because we actually can take every x and y.
But I mean, depending on what series you use.
Yeah.
Because it will change.
If this series we need the condition is lower bound is need to be bigger than the half of the upper bound. But I think uncountable sets and everything has a lower bound distance and upper bound distance. What is that?
Not sure.
I don't know. I don't think that because everything uncountable we construct is dense.
Okay. Think about it.你们上过 ALA 吗？
没有，我们都没有看过。
上过什么
ALA
你知道吗？招生他们看到你写有 Q， 就在那边问我们是不是要把这个放在 exercise。
哪一个？
他偏偏的 hypothesis。
你 prove 得到的话就原地毕业。
不是 prove 得到应该拿菲尔兹奖吧？你还没到40岁就有招生。
那个因为我们的点是要就是
我们要 confirm 一下几个东西嘛。第一个是你昨天问我要 confirm 的是要谁，你如果有东西你要是问你要给谁？
对，不是说我直接跟他沟通就好啊，你就负责，然后他要给你检查就给你检查，这样
也行。
啊，这样你就不用来。
OK，
主要是你先把试的弄好了，你把它先给我，然后接下来我自己后做就好。只是那个 exercise 的部分可能
你要
我
我把
再找
你要把我加进你们群也可以，我可以直接在那个群。
我没有群的。
你不是讲你们有群？
他说要建群，他没说有。
对，但是建了我也是建给 homework 专门讨论 homework，
OK
我不会去讨论跟他把我们的讨论跟他们去讨论。
OK 了，这样我就对你就好了。
对，
或者我们也建个小群，可以在群里。
可以啊，也可以叫建小群，可以建小群啊，建一个 team 这群啊。
可以
OK，
因为还没有问草定。
哎，问你，对吗？马太博上这个课的时候，真的也是照着他那本书里面上的。
这风格就是照着他说。
我感觉你上了蛮多东西啊，我感觉你去掉蛮多东西。
我不懂他讲了什么东西。
我去对照一下，首先你前面那个 introduction，就你放在 Simon 那题，它不是它上面有一个一个 section，然后他还讲了，比如说我看他你有一个没讲的是那个 P_N 和 R 的 coordinate。
对，但是你可能要经过几步路，从这边就会到。
也。
对。
然后这个就是还没登屏了。
喂，
他很适合做讲师，我发现。
就像你什么，你知道吗？你去把老太婆的书背出来，他的名字你都能考。
对吧？你全部是把书里面的，你没有教的。
可以带其实。
可以带吗？
你抄。
Yes，我想问一下，就可不可以用另一种办法证明
哪个
cardinality？A 的 cardinality 是 B 等于P_A？
怎么样？
我们可以假设这个 set A 可以写成 A 吗 ？U2 U3？
不一定，因为它可能是 uncountable 就不能够了。
哦，那应该不行。
你可能可以对 countable 的做吧，但是我们这里要包含 countable。
还有手劲啊！
哇，你上个礼拜不是抬肚子痛好没？有喝吗？你 try 看。
就是这一个 X 是什么意思？这是怎么想出来的？
我怎么想出来啊？你一定是不要这个东西存在，不要让有一个 B such that FB 等于它。你不要让这一个成立，因为这个不成立，你才可以找到一个它 map 不到的地方，然后你就专心让这个不成立就好。这个是其中一个方法啊，我不知道有没有其他些。这是其中。
Yeah, thinking impossible. Yeah, because if every point is isolated, you can find an epsilon, then they contain a rational. Then the cardinality is less than equal to Q.
Okay.
Yeah, so it can be uncountable.
It can be uncountable.
It can't be.
It can't
because
be. Okay.
it's injected with Q.
Okay.
Yeah, every element is isolated, so you can find an epsilon neighborhood that only contains the point, and this neighborhood also contains a rational. Then you back to the Q.
Okay.
You have injection, but it's count.
Okay.
You can't do that.
Can.
就是这个是，我不明白他这个，
就是你这个意思是说这个意思啊，
对的，
这意思就是说你去找一些 A such that，因为这个 F 嘛，肯定会把 A 送去一个 subset。 然后 then 你就可以去看，你去找所有不在那个 FA 里面的
这个可以理解成不等于吗？
不在里面，因为你看，因为这个 A 啊，肯定会送去一些 set 啊，它因为这里的 element 是 subset 嘛，对不对？
就送到一些 set 里面不包含这个 element。
对，不同包含自己，它可能被送去 B、C 嘛，然后 then 这个就是我要的 A 咯，这是其中一个我要的 A。
我一直在想
OK， Hello，
对，肯定的呢。它这次就是一个 example，是要多少？
你那个海博那些什么东西？那个跟你讲有个 P 吗？
那个没有 P， 没有 P，
他就跟你讲，
这个猜想是说没有 P，
没有中间的东西，没有，直接就跳到 C。
但是这个猜想到底是对还是错，我们没有办法用目前的测度这个。
hypothesis， 我们都不知道它对错，
我们根本没有办法讨论它的对错。
对，不知道对错。
哎，也可以这样讲啦，但是呀。Okay, let's start. Okay, finally we're gonna move to second chapter. Okay, second chapter actually is the key of this class. Later on we'll build things on chapter 2. Okay. So the plan is we'll start with metric spaces. Okay. And then we will move to topological spaces. Okay. Topological spaces. Okay. And then we'll talk about function. Okay, function between spaces. And we have spaces, we have function. Then this is called a category of topological spaces. Okay. Again, we have top category here. Category of topological bit spaces. Okay, so what's category here? It is object and function. Okay, so we have object, we have function here. Okay or not? So we have category. Whenever you see object, you see function together, these two constitute a category. Okay, category of topological spaces. Right, so metric spaces is what? What is metric? Metric is what? 测量 distance. Okay, distance 长度距离 okay, distance. Okay, so in MA2 you will just look at distance in Rn. Okay, so Rn is an example of metric spaces. Yeah, so later on we'll look at different distance function on Rn, and then you'll see that the open ball will look different in different metric. After that, then we will abstraction to topological spaces. We don't want to play with epsilon delta anymore. Okay, we just play with openness and closeness. Okay, openness and closeness. So basically, we are moving from epsilon delta to openness and closeness. Okay, no? And open and closeness here basically is just set theory. Is it inside there or not? Inside there or not? We can define intersection using elements inside the set, in whole set, something like that. Set theory. Alright. Okay. For example, we define the number less than or equal to using injection, also set theory. Okay. So this class is basically set theory. Okay. Basically set theory. All right. So done with it. Let's start. So we're gonna start with metric spaces. So we have to look how to it. Why? Okay. So let's define what is a matrix spaces. So there are two words here, metric and space. So here got two tuples. Okay. Tuples here. So what's this tuple here is a set. Okay. Together with a distance function, okay, called D. So you have a set, you have a function, distance. Okay, 要怎么想象这个东西啊？适应，可以不要叹气嘞，给你机会来。啊，你想一下，有一个 set， 有一个距离是什么意思？不要，我要问你先，我要问你先，把它生活化一点啊，什么意思啊？有一个 set， 你活在整个 set 里面，你看这么多 set， 什么是 distance？ 你就带着一把尺这样走来走去就对了。OK， 拿去量。OK， 等一下我们会有不同的尺给你看的。OK， 好。So what does this ruler have to satisfy here? Okay. So there are three properties that this ruler, the distance function here, need to satisfy. 可以量出 negative 的东西吗？ Cannot, huh? Okay, so there's something called positivity. Okay, no matter what 2 points you measure, should be greater or equal to 0. Okay, negative. And then if dxy is 0, so what are the things that have distance 0? If and only if they are the two same points. There's only one case only. Second, symmetry. From here go to IOI, and from IOI to here is the same distance or not? Could be different now if you use the different road. Okay, but the shortest distance is the same. Okay, dxy equals to dyx. Okay. 3. Okay, this one very important. This is called the triangle inequality. Okay, this triangle inequality teach you how to walk shortcut. dxy is always less than or equals to dsz plus dzy. Can you see triangle here? Can you see triangle now? Huh? You got 3 points, right? X, Y, Z. Okay, the distance from X to Y is always less than, you go to Z first and then go to Y. 合理吗？合理啊？ Okay, this one teach you how to walk shortcut. Yeah. Okay. But there's another thing called pseudo metrics. There's another thing called pseudo metrics. So pseudo metrics play around with positivity here, meaning this if and only if is not always true. Okay, you could have different points that have distance 0. And then this is very useful in general relativity. Okay, 2 different points in space could have the same, not same distance, as a 0 distance. Okay, and 0 distance. Okay, I think you have met this pseudo metric in your assignment later. Okay, right. Let's give some examples of metric space. For example, Rn 删了吗 ？MA 2有刚刚上吗？没有没？没有进 ？Seriously？ 你们不是进了双条大没 ？What？ 你们不是 show open close 那天给我看 ？Then what's that? What's that? Bow You don't have distance. How to make bow? You should have distance first, right? Okay, so what's the distance in a Euclidean space? We call this a Euclidean space. This is the usual x1 minus y1 squared plus x2 minus y2 squared and up to xn minus yn squared square root. Okay, so this is like the generalization of triangle inequalities. Yeah, so okay. Good. Okay, so this is the generalization of the triangle inequality. Right. So if I put s, y, z here, s squared equals to y squared plus x squared. Okay. Make sense? Got question? Okay, so for this, you need to check the tree property here, positivity. Is it always greater or equal to 0? Yes, right, because we are squaring all the difference and then add them up and then take square root. Still positive. Okay, when this number equals 0, okay, you need to prove that only when x1 equals to y1, x2 equals to y2, and so on. Correct or not? Because you are adding out a bunch of positive numbers to get 0. So the only way to get is the adding up all the 0 together. Okay, later we'll talk about inner product space. Okay, and then symmetry. Is it symmetry or not? If I swap x1 and y1, symmetry, right? Because you squared it. Triangle inequality. You can do it in a more general setting, which we will discuss now. So we will do triangle inequality for T induced by an inner product. Okay, so this inner product we consider as xy equals to x1y plus x2y2 plus dot dot dot. Okay, we will do in this case here. You can try or okay, I put a or here. Just show directly. But I think it's the same way, if I'm not wrong. Yeah. If you go these two ways here. So we're gonna motivate inner product now. So actually, second example I'm gonna show you is in general, inner product spaces are metric spaces. In particular, known space is also metric space. How many of you have went through ALA before? How many of you? ALA? See? About half of you. Okay, let's see how we define a metric. Sorry. Yeah, how we define metric from these inner product here. Okay, let's see. So what's the inner product? Do you still remember or not? You still remember inner product? Okay, first ask a question first. Inner product defined on what space? Vector space. Okay, I take two vectors, right? Give you a number. Okay. So in particular, you see from our Rn is perfectly good at vector space. Okay. So actually you can show that it's induced from some inner product, which I've written for you already. So what's inner product? I write things down. I don't want to copy it. Just show it to you. So what's the definition of inner product? Let's remind you. I think the first place you see is LA1 or LA2? 2. Okay, 2 only see it. Okay. Right, so let me show you what's the definition of inner product. And then we can compare how similar the definition of inner product and matrix function, matrix spaces. Okay, so what's the inner product here? So basically it's a function, okay, that takes in two vectors, give you a number. Okay, taking two vectors, give a number with three property here as well. Again, there are three property here as well. So first, you see, first quite similar, huh? Okay, if you take 2v, you compute the inner product should be greater or equal to 0. If it is equal to 0, that means v is actually 0. Okay. Second is the conjugate symmetry. Okay, because sometimes this value will live inside complex number. So it's not just symmetry, but conjugate symmetry. Okay, you need to add in the complex conjugate on the other side. Third one is bilinearity. So you can it's bilinear on two variables here, but it's enough to just define on one side. Okay, because you can use the second conjugate symmetry to get the other linearity out. Okay, so this is inner product. Okay. So for every inner product, we can go to the next step. We can define a norm space. Okay, we define a norm. Norm is length. Okay, norm is actually length because you are computing inner product between you and yourself. Correct? You still remember a formula about inner product? S dot y equals to what? X dot y equals to what? Length of x times length of y cos theta. But what's the angle between yourself? 0. Cos 0 is 1. Okay, so you get length of v squared. So that's why there's a square root there. You don't want the square. Okay, so it's the length of inner product of v. And then this norm will satisfy this three property also. Okay, what's the first property here? So if v is not a zero vector, obviously your length must be greater than 0. Okay, otherwise, it's very contradicting. Second is positive homogeneity. So what it means here? So meaning if you scale your vector by some k, your length is also scaled by the scalar. Okay, without any sign. Okay, you just scale it positively. Correct? Otherwise, your length becomes negative. Okay, there will be a trouble. Third is also triangle inequality here. Okay. So if you add up your vector first and then compute the length, it's actually less than or equal to the sum of the separate length. Okay, so this is normal. So from inner product, we can go to norm. And then there's a very famous inequality, Cauchy-Schwarz inequality, that relate these two, relate inner product and norm. Okay, relate inner product and norm. Yeah. Okay. I think this inequality is important for you to show triangle inequality later. But anyways, that's not my point for now. And then, but how to go from norm to distance? What is distance? Distance between me and Adrian is what? You take a line, draw from me to Adrian, and then you measure this line. Okay, so you are taking v minus w and then computing the norm. Okay. So in turn, this is defined using, you can be defined using inner product. You can check that the metric, okay, yeah, the metric defined by this square root on this inner product here satisfy the three matrix property. Okay, okay. Okay. And see if I check triangle inequality for you or not. Yeah, I think follow from this triangle inequality. Okay, I left it for you to read it. I don't want to do calculation in class. Okay, I leave it for you. Actually, these three pieces is what I written from one of the quantum mechanics seminar last time. 2 years. 2 years. 1 year ago. 1 year ago. Okay. Okay. So let's look at more examples of metric space. So I don't think any of you take differential geometry this semester. So there's one example from differential geometry. About curve and surfaces. So if you take any smooth surface here. Okay, so what does it mean by smooth? 涂了很多 mask 没有啦，开玩笑。Infinitely many differentiable, infinitely differentiable. Okay, infinitely differentiable. Okay, if this surface is infinitely differentiable, So how do you compute the distance between 2 points here? It's actually the length, okay, of the shortest path that join X and Y. Because you could imagine, like what I gave you an example just now, right? There are plenty of way, not plenty of way, a few of way to go from SMUM to IOI, right? Okay, which one is the shortest one? Okay, we take the shortest one，直接到连过去，管它有路没有路，有路了，要有路了。OK， 最短的路 ，OK， shortest path. Because why we say shortest path here? Because in different geometry, right, you could have a different shortest path. 可能在不同的 in different spaces, the path look different. The shortest path look different. So this path, this shortest curve here has a magic name called geodesic. Okay, so this is the item that you study in differential. Okay, the geodesic in our space, Euclidean space, obviously you know, right, is a straight line. Okay, but in different space, if in hyperbolic space, spherical geometry space, I think someone learns spherical geometry, right? FYP, low how? What is the shortest curve in spherical geometry? I think you learned something called great circle, right? Yeah, those are the shortest path on sphere. 它是有弧度的，不是直线。直线的话，你就要穿过那个圆圈，你只能够在那个 sphere 上面跑嘛。Okay, those are the shortest path. Okay. All right. So let's go to the next one. Okay. Next example, we're gonna send post. You will be a postman now. Yes, postman. Okay, so this is what we call a French metro. 就是法国的地铁啊 French metro, or sometimes they call it a post office metric. And so what's this post office metric here? So the picture is like this, okay? So you are sending a letter, okay, from the office, go out, come back, get the letter, and then go out and go in. Okay? Does it make sense? Okay. The metro, you need to come back to a bus station first, right? Only go out. Okay, so this is the metric here. You have to come back to one point first and then going out. Okay, so how to define this? So let's say we restrict our X here to a smaller set. Let's say X in R2 such that the Euclidean norm, so this is the Euclidean norm, is less than 1. So here, obviously, you get a sphere here. Not sphere, everything less than equals to 1, so you get a this. So we define a new distance here. So how do we describe this kind of distance? You need to come back first, and then go out, come back, and go out. Okay, before you can go to the other point inside your space. Okay, so what's the distance here? So if the next destination you go is in a scalar multiple of where you at, okay, so what you do is you just take the difference between X and Y and then compute the length. Okay, otherwise you need to go back to 0 and then go up again. You can only move in straight line. Okay, in other words, you only can walk in straight line. If you are in the same line, you don't need to go back to 0. Okay, if you are not in the same line, you need to go back to 0. Okay. Okay, so let me write in word what this means. So this metric says that when let me finish now. 我们俩插话看。我写什么？哦，等一下我写什么？哦 ，otherwise 我忘记写。哦，对，我忘记写 T 也是。Thank you. So where's the T 呀？T should. 哦，这个不是加减，这个是 T. Not just plus minus, you can scale it any way you like. So this metric demonstrates that the transport is in straight line. Okay, if it is in straight line, 你可以直接去。Okay, If it is not in straight line, you must come back and then make the turn. Okay, you can only turn at the 0 point, the origin. And the origin is the center of commuting. Okay or not? So this will define the French metro metric here. All right, next. So I'm giving you a few examples of how we can play with a metric here. So if you like, you go back and do practice. Show the three property for all these metric. Show the positivity, symmetric, and then triangle inequality. Okay, next. The p-adic metric we can put on Z. The usual metric on Z is what? Just the difference. 2减1 3减0 like that. Okay, but we're going to put a different metric on Z now. We call it a p-adic metric. Okay, so what's this p-adic metric here? So let our set to be Z now. And then what's P here? P here, what do you think? If I write P, what does it suggest? I want to pick P to be a what? Prime. Yes. Okay. So P usually denote a prime. So for a fixed prime, right? If you take different X and Y in Z, such that there are difference. If there are difference, right, in analysis, what you can do, if you have two different points, you should look at the difference. What's the distance between X and Y? And you can divide by P. Keep dividing by P. Okay, until that it is a multiple of PK times N. This. I think we can. Cannot. 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 This is prime factorization theorem, right? Prime number factorization theorem. Hey, anyone know what is prime number factorization? Every number can be written as a product of prime. I'm just counting how many prime number P inside there. Can you get example? For example, if P is 2 and then X minus Y is, let's say, 13. Okay, try 13. So can what's the PK you can write here? What's the N you can write here? I haven't tell you what's N here. N here is something in Z only. K have to be natural number, and then N is some Z. Okay. So 13, how to write as a product of 2 times some N? Right? Want to try? I can. Any 2 factors or not? Yeah, more than 13. 2 to the 0 times 13. So actually this K have to include 0. Okay. Okay? Yeah. 1 times 13. Okay now. So this decomposition is based on every integer or every integer can be written as a product of prime numbers. You are just compute how many factors of prime number. Does it make sense? For example, 4. How about 4? 4 can be written as 2 to the power 2. Any non-significant one. I mean significant one. For example, 12. 12 is equals to 2 to the 2 times. Okay. Yeah. So for those that are not factor of P, I cannot say factor of P. They are not P factor, then you just move it to N. Then just move it to N. So we will say that this N actually is not divisible by P. Okay. Those that are not divisible by P, you just move it to N. So how to define D here? So this is a very clever construction here. Okay, based on this decomposition, we'll define that the distance between X and Y to be k plus 1, 1 over k plus 1, or k plus 1 inverse. Okay, if x not equals to 1. 0 if x equals to y. Okay, makes sense or not? What is this trying to do? Can you see or not? Can you see what this is trying to do? What happens if x and y are very far different? You could imagine that it could have more factor of p. But you see, if you have more factor of p, the distance is divided by that power, meaning what? They're getting smaller. Okay, so far number become closer inside this metric. Okay, so this is the metric we can define on Z. Okay. In fact, this is a main subject that people learn or study in algebraic number theory. And this is the main subject. Okay, but this guy doesn't satisfy, and maybe it's hard to check triangle inequality, or actually it satisfies a stronger triangle inequality. How to spell strong? Stronger triangle inequality here. So what's the stronger triangle inequality here says? So actually, dp of xy is less than or equal to the either dp of xz or dp of zy. It's already less than or equals to one of them. Okay, not the sum of them. One of them is enough to cover the inequality. Okay. So you could imagine how we get real number from Q. How we get real number complete. How to complete rational number to how to complete rational number to real number. How to do that? How? Sorry, I give one way. 全部人这边应该是上过 MA1 的哦。OK， 应该大家都懂了。Well, how do you complete? How do you find? How do you build irrational using rational? What closure? How to close? Okay, so you see irrational as a limit of a Cauchy sequence. Okay, but Cauchy, how do you measure Cauchiness there? What's the distance you use there? Euclidean distance. What if you use this metric distance and complete it? Add in all the limit. What do you get? What are the p-adic limit of Z? What is Z bar? Okay, you add the limit. Okay, yeah, this is what they study. Okay, in algebraic number theory. What's the answer? I don't know. Oh, they call it p-adic numbers. Okay, they call it p-adic numbers. So if you try to complete the Z under p-adic metric, I will define what is it, but very metric. You will get what called the p-adic number, ZP. Okay, so morally it's the same. You just take Cauchy sequence inside this metric. Okay. Equivalent class of Cauchy sequence. All right. Okay, before we finish, we really need to draw some ball before end. Okay. Let's see. All right. So instead of talking about metric, I can tell you what's the norm, right? Once I tell you the norm, you should know how to get the metric. Norm is just telling you how to measure a line. Okay, but how to get a line from distance, you just take x minus y. Okay, you can take the length already. So what are the other norms you can get here? Okay, so if I tell you norms, you automatically get a metric. So for example, P norm, okay, this is LP. Okay, LP norm. So what is LP norm here? So if I fix different P, okay, so this P can be ranging from 1 to infinity. So what we're gonna do is we're gonna alter the power that we can use here. So for example, we can take the sum of the absolute value of xi to the power p, and then sum all the coordinate out, and then take p root. And so in particular, Euclidean norm is L2. There is a L2 norm. The Euclidean norm is a L2 norm. The other norm, we call it sup norm, okay, supremum, L infinity. So we denote it as the length of x1, x2 up to Sn. This is called, what's this norm here? Actually, this is just take the maximum of the absolute value of each xi. Okay, you take whatever is larger in their absolute value. Okay. You understand this norm here? For example, what is the sup norm for 1 and -2, for example? 来问一个人，test 一下。谁啊？谁？点谁？点谁？罗浩，罗浩，罗浩，来点名。Wow, what's the sup norm for 1 minus 2? Maximum of their absolute value. Maximum of absolute value of 1, absolute value of -2. Okay, so which one is larger? 2. Okay, so the length of this 1 minus 2 is 2. And the length of this in Euclidean space is what? Can you compute it? In L2, can you compute what's the length of this L2? 2 here. 1 square plus minus 2 square root. What do you get? 5. Which one is larger? 5 larger. Yeah. Okay, because 2 times 2 is 4. Square root 4 is less than square root 5. Alright. So sup norm is smaller, oh? Okay, under sup norm, this length is smaller. What else? Should I introduce something else? Hey, I want to ask you guys, did you see this in your PDE or something? So let's define norm space on the continuous real value function. Okay, continuous real value function. Define on the interval AB. Okay, define on interval AB. Okay, so how many ways you can define norm here? So first way, the easiest one is sup norm, again, sup norm, but this one is defined on function. And how on earth you Lydia 讲量 function 讲量有多少个字吗？有字，为什么 function 有字 ？function 哪里有字 ？piecewise function 怎么样有字？Okay, so we'll define it as a sup f here. So instead of measure function, function just tells you where the element should go, right? Instead you need to measure on elements. So how to get elements from a function? So you have to apply your f to some element first. So you just apply f to some elements and then measure that elements. Can or not? Can measure the elements or not? Because your function is a real value function, meaning what? This function should land in where? Land in real numbers. So you just use the Euclidean norm there, whatever norm that you have there. Then what do? You compare all the fx you can get from your domain and then take the supremum, because this is just a bunch of real numbers. In MA1, I give you a bunch of real numbers. Go and find me the supremum. Then let me find the upper bound, least upper bound. Okay. And what else? We can define L1 norm. Okay, so what's L1 norm here? Well, L1 norm here is the integral of from A to B on the absolute value of f because we don't want things to cancel out. Okay, make sense? It makes sense or not? Okay, just the integral. Integrate. You get a number, right? You get a real number, right? So L2 norm. L2 norm here. What's L2 norm here? You are integrating the square of your function and then taking square root. Okay or not? Okay. All right. So we're gonna end soon with one last definition and example. Okay. Yes. What's the difference between L1 norm and L2 norm? What do you mean? That looks very different, right? What do you mean almost the same? The square is outside, bear in mind. The square is not inside. If it is inside, you cancel with x square already. Right? It's outside. After you compute the what? Integral only you take square root. Okay? For example, okay, let me show you some examples. How about I let you see this kind of f, the easy f, y equals to fx equal to x. Okay, so if you take the modulus of f, what do you get? You get a v shape. Okay, but if you take the square of this x, you actually get x squared. X squared looks like what? Is the integral of x squared same with modulus f or not? Yeah, they should compare to different things in general. Okay. Okay. So members of general metric space we often just call them points. Okay, just call them points. The elements, in other words, but we call them points. For example, you are point. Okay, in this world, you are just a point. 你只是一个点嘛。Okay. Although there could be a function, set, or different mathematical object. Okay, right. Just now we just define norm on set of points of element or function space. Okay, they could be function, could be set or numbers. Okay, but in general we call them points. Okay, these are points in our metric space. Okay 吗？有一个点。So if it is a 点, then everything we're gonna draw as a point now. Okay, we're gonna draw everything as a point. Okay, let's finish this. OK 吗？你们赶时间吗？你们可以再借我5分钟。赶时间了。OK， 所以赶时间谁可以先走？还是全部要走？OK， 我觉得这个很好玩，我一定要给你们知道先。OK，so let X be a metric space. Okay, we can define a very interesting object. You're gonna leave it for the whole semester here, called open ball. Okay, this open ball here is determined by two things. One thing is the radius. The other is, anyone want to know? Yes, is the center. Okay, you need a center and a radius to build a ball. Whenever you talk about a ball, you need to tell me the center and radius. Okay, how to define this? So this is called a BRX here. Okay, BRX. So what are in here? So every point in X such that distance between X and Y is less than R. Okay. So if you want to draw in the usual Euclidean spaces, every point with X needs to be less than R. Let's say this is R. Okay, so all your points will live inside here. Okay, not including this outermost distant point here. Let me draw it. Okay. So it's open. Okay. Where the point that's equal r, okay, dxy equals to r, we don't take those y. Dxy equals to r, we don't take. Okay, only strictly inside. Okay, does it make sense? Okay. So now I'm gonna leave you a question here. So let's find an open ball that's centered at 1, 2, okay, with radius, any radius, let's say radius equals to 1. You can do it for any radius. Let's take a bracket here in R2 with 3 matrix here. Okay, one is the L2 metric or induced by L2 norm, which we call the Euclidean metric. This is the one that you are very familiar. And we're going to try it on L infinity, the metric norm. We'll use the sup norm. Okay, and the L1 metric. Yeah, let's write down the equation that you need to satisfy, and then we think of the picture that you need to draw. So let's try it. Okay, so L2 norm, right? So meaning what? All the point that is in distance with 1, 2, which is less than or equal, no, just strictly less than what? L infinity, I just now know how to do one. Okay, what do? You are taking maximum of the difference in first coordinate and the difference in second coordinate. Less than also less than 1. How about L1 norm? What's the difference between L2 norm and L1 norm? The power there gets substituted by the number n equals to 1. So here you will just get the absolute value of x1 minus 1 plus absolute value of x2 minus 2, which is less than 1. So what are all these points looks like? Okay. I think this guy you know, right? If I put equal 1 here, what's this? Circle, huh? Okay, so here the circle with radius 1 centered at the point 1, 2. With radius 1 here. Okay. How about the maximum? X1 minus 1, x2 minus 2. What are all the points that satisfy this? Can you start with some point that you can work on? Or to make life easy, okay, make your life easy a bit. Okay, I make your life easy a bit. Let's center it at the origin. What are the points that satisfy the 2 coordinate less than 1? What could happen here? What number you can take for xi and x2? Yeah, 0 to 1 like this, 0 to 1. Okay, s2 also 0 to 1. Can you take negative value? Can, huh? Because absolute of negative 0.5 also less than 1. So you actually can go from negative 1 to negative 1. If you take the product of these points, what do you get? You get a square actually, right? Okay, so in this case here, you actually got a square centered and 1, 2. So you get a square here. So if you shift it up, what do you get here? Let's see. If you shift it. So if you shift this up, what do you get? Your xi will go from there. What do you go from? What do you go from if you shift it? Shift this. Is it 0 to 2 here? And then So this side here is 0, this side here is 2, and then you go from 1 to 3. Okay, you ship it. Okay, last one, before going back. About this one. This one a bit tricky, or this one. Again, I made life easy a bit. So let's look at the center at origin. Let's draw this. This one, I left it for you. Okay, what are the points when you add up is less than 1? What are the possibility? Or before guessing the range, can you give me some point that satisfy this or not? We start from there. Obviously, 0, 0 works. Fair enough. What else? 1/3, 1/3. Okay. And then 1/3, 1/3. Okay, let's decide some point that you can use here. How about maybe it's easier to ask what's the point that satisfies the length of x1 plus length of x2 equals to 1. Can we guess this first? These are the points we don't want, but let's guess what are these points first. Easier to check. It's a square. It's a square. Huh? What? Oval? What? Oval like this oval. Is this what you mean? Square is a square. How do you determine this square? Where are the four vertex you can pick first? 0, 1, 0, minus 1, 1, 0, sorry, minus 1, 0. Okay. And then where is the diamond? You got a diamond here. So if you try and get the line equation for this square here, that should satisfy this equation here. Is it true? So what are these lines here? What are these lines here actually? X plus y equals to 1. Okay, anything else? Minus x plus y equals to 1. X plus minus y equals to 1. Minus x minus y equals to 1. Should be these 4 lines. Okay. And then what you need to take is everything inside this. Outside this kind, you should see that it doesn't satisfy the inequality. Okay, so how many type of ball you see here? So there are 3 types, 3 different types. Okay, if you change your metric, your ball will change. So it's very sensitive. Okay, so your ball is not always sphere. Okay, it could be something else. Square, could be other things. Depends on what metric. Okay, any question before finish? Okay, so we extend our assignment to next Wednesday, so make sure you spend time doing it. Okay, if you have problems, come to my office hour. See you next week.